going to go back into the second day of 6.3 on logarithms, and today we're going to look at common logarithms and natural logarithms and start evaluating some of these logarithms, okay? So a base 10 logarithm is called a natural logarithm because in all of our number systems we use base 10, right? 10, 100, 1,000, and so forth. And so a logarithm with base 10 is called a common logarithm, and it's written as just log x. So when you don't see a base here, that means it's just a base 10. It's just automatically assumed it's a 10, okay? Base e logarithm is called a natural logarithm, and it's written as ln of x. And so when you see an ln here, that's automatically assumed it's just base e, okay? So the expressions log base 10x and log x means the same thing, as does log base e of x, and natural log ln x means the same thing, okay? And so you can kind of see back here, natural log of n equals x can be written as e to the x power equals n. Log of n equals x can be written as 10 to the x power equals n. And then logarithm of some other base a of n equals x is written as, a to the x power equals n. And so this is just a typical log with any other number. Common log is base 10, natural log is base e, okay? So that you might look familiar on one of those problems we had on last Excel. So what is the value of the logarithm expression to the nearest thousandth? Well, most calculators have keys for the common logarithm and for the natural logarithm. And so we can just plug in here and say, what is the log of 900? And we're going to round this to the nearest thousandth. So it's 2.9542. Okay, so 2.9542. 2.9542. Okay. And then you can check the writing expression by saying, well, 10 to the 2.9542 power should be approximately equal to 900. And so you can always double check that, right? So we can actually take our calculator here. We can plug in 10 to the 2.9542, and we should get about 900, and so you're very, very close to that. Okay, so we actually carried out all those decimals, that's where we'd be. Okay, so these calculators can calculate logarithms. All right, so what about a natural logarithm? So let's go ahead and calculate that. What is log base e? So if this is a base e of e, this should be equal to 1, right? So anytime we have the same base as the argument, it should be equal to 1. So log base e of e, boom, it's equal to 1, okay? And so this is equal to 1. And again, I could say e to the first power should equal e, and of course that checks out, right? Okay. So how about log of negative 1.87? So can we take a natural log of a negative number, right? So natural log of negative 1.87, and we'll close our parenthesis here, and see, it goes error. Remember, we cannot take logarithms of a negative number, okay? And so this is undefined, if you remember that from our last lesson. So undefined. And the same thing in a calculator, if you put it in there, it'll give you some error notification like, yeah, you can't do that. Knucklehead, okay? All right, so you might want to pause the video here and just try to evaluate these in your calculator, get used to those buttons, and round these to the nearest thousandth. So let's go ahead and see what we do here, okay? So for this one, we have log of 321. That's 2.06507. 2.507. Okay, 2.507. Right? How about natural log? Natural log of 1215. We got 7.102. So that's about 7.102. This, of course, is going to be undefined. Right? We cannot take the log of a negative number. So how about here? We have natural log of 32. That's going to be 3.466 if we round up. Okay, 3.466. Okay. How about natural log of 10? Since this is base 10 and the argument is also 10, that should just be equal to 1, right? Same thing here. My base is e and my argument is also e, so that's going to be also 1. So anytime you have the same base as the argument, that's going to be equal to 1. Okay? So now let's take a look at how do we solve some of these, and so we're going to solve with these common bases first, and then later we'll solve with other bases. But so if we have a common base right here, we have our variable in the exponent. So when I have our variable in the exponent, we're going to use logarithms to remove the variable from the exponent, okay? So we're first going to convert this to logarithm form. So we're going to say log base 10. So instead of just putting base 10 there, I'm just going to leave it as log. So remember, it always equals my exponent, right? So it's going to equal x minus 1. That's my exponent. And it's going to equal log of 25. That's my argument, okay? Well, I can calculate the log of 25, right? So I'm going to come down here and I'm going to find out what is my log of 25. And that is going to give me, I'm going to keep this in about the thousandths, okay? So 1.398. So I'm going to say 1.398 equals x minus 1. And then I just have to finish solving for x, add 1 to both sides. So I get 2.398 is approximately equal to my x there. Okay, so that's how we use logarithms to solve. Now this has a base of 10, and so that would make it makes it really easy to use the log, not the common log, to solve that. Okay, so now this time we actually have a logarithm form. It's a natural logarithm form. So how do we solve for x here? So this is when we actually remove the logarithm by using exponents. Okay, so we have a base e, and so we're going to write this as e to the 4th power, because that's my exponent. E to the 4th power equals 2x plus 3. Okay, well, we can actually calculate e to the 4th power, right? So we're going to go second function e to the, boom, into the 4th power. Okay, that's 54.598. So at 54.598, they want to the nearest thousandth, so I'm keeping things to the nearest thousandth, equals 2x plus 3. And now I just need to solve here. Okay, so I'm going to subtract 3 from both sides. This becomes 51.598 equals 2x. And now if I divide by 2, right here, you'll just have to trust me on this. It's 25.79. Well, actually, here I'm going to do it so you can just see how our rounding is going here. So we're going to have to first, we're going to subtract the 3 here, and then we're going to go ahead and divide by 2. Okay, so 25.799 is my nearest thousandths, right? So 25.799 is approximately equal to x. And that's how you solve when it's in logarithm form. Now we're going to be strictly solving mostly natural logs and logs today. Next unit, we'll start learning how to solve any kind of logarithm, okay? Those will be simple. So go ahead and pause the video here. Try to do this on your own and then come back and check and see how you do. Okay, so we have a logarithm here, a common log. So we're going to write this base 10 to the 2nd power. That's my exponent, equals 3x minus 2. So that's 100 equals 3x minus 2. I'm going to add 2 to both sides now to just solve for this. So 102 equals 3x. And then divide by 3. So what is my 102? Put my calculator up here. 102 divided by my 3 is going to get me a 34. So 34 is equal to x. And there is my solution. Okay. What about this other one over here? So now we have an e. Okay, e. So we're going to have to use a logarithm because our variable's in our exponent. So when our variable's in our exponent, we need a logarithm. Since we have a base e, we want to use a natural log. So natural log, right? A base e is going to equal my exponent, so x plus 2, and my argument is going to be 8. Okay, so my natural log of 8, I can actually calculate a natural log of 8. Bada boom, bada bang. So you have 2.079. So 2.079 equals x plus 2. Okay, then I'll subtract 2. So I'll end up with 0.079 equals my value of x. And there you go. Okay, so again, we have a logarithm where we need to actually solve for x. We use exponents to evaluate that. Or if we have a variable in my exponent, we use logarithms, so like the inverse, right? If I have an exponentiation, I use logarithm and inverse. If I have a logarithm, I use an exponentiation. So remember, those are inverses, right? Logarithms and exponentiations are inverses of each other. So we use those to undo each other, okay? So let's take a look at a little story type problem, I guess. So this just says the seismic energy X in joules can be estimated based on the magnitude M. of an earthquake by this formula right here. What is the magnitude of an earthquake with a seismic energy? So that's going to be my X value of 4.2 times 10 to the 20th joules. So this is my X value, right? That's what my seismic energy is here, X, okay? So I'm going to plug this into that formula, 4.2 times 10 to the 20th equals this guy here, 10 to the 1.5 m plus 12. So now what we have here is an exponentiation because I have a variable in my exponent. So we're going to use logarithms. I want to note that my base is 10. Okay, so I'm going to use a log of base 10, which is going to be just a common logarithm. That's going to equal my exponent, 1.5m plus 12. And so my argument is this 4.2, that's a 4.2 times 10 to the 20th. Okay, well, I can evaluate that guy. Right, I'm going to go ahead and clear this so it doesn't look so conglomerated. Log of, and I have a parenthesis there, so I'm going to say 4.2, okay, times 10 to the 20th power. And I will close that parenthesis there. Whoops, that's kind of a weird parenthesis. 20th power, I have to move over to close my parenthesis. There we go. And then I can evaluate this guy. It's 20.623. 20.623 equals 1.5 m plus 12. And from here, I just have a nice equation. I'm going to subtract 12. Okay, so I'm going to do this as I go so I don't have to do it all in one step again. So I'm going to subtract 12. And that's going to give us 8.623. 8.623. And then now I'm going to divide by 1.5, and what is that going to give us here? I'm going to divide by 1.5, and that's 5.7. Okay, so 5.7 approximately equals m. So we come up here, it's going to be somewhere right around here on the magnitude, 5.7 on the magnitude, earthquake magnitude scale. Okay, and so that's just a little application problem. So here's just a little summary of exponential form, logarithm form, what it means. And then you have an Excel and Google Classroom, and I will see you all in class. Thanks so much. Bye-bye.